so our initial situation, we've got a spring with these two masses A and B attached to it. We stretch it out to location 1, and then we're just going to let go. So what's the starting speed?
The starting speed is 0, right?
It starts off at speed 0 because we're not giving it a throw or a shove or anything. We're just pulling it to this location, holding it still, and letting go. So it starts off at speed 0, and an initial location, x initial, equals x1. So x1 is our starting location, 0 is our starting speed. Then it's going to oscillate for a while. Maybe it oscillates once, maybe it oscillates many times, we don't know. But at some point, while it's on its way back out, the glue breaks as it passes through equilibrium. And we want to figure out at that instant, what's the speed? So if we treat this as the final situation, x final is 0, v final is some unknown speed. And we want to find that speed. So what's changing from initial to final? What types of energy are involved here?
So we have the potential energy of the spring mass system.
Yeah, spring potential energy. And how can we tell that that's changing? What's the indicator for that?
The displacement from equilibrium.
Which we'll write as absolute value of x, because we don't care whether the x value is increasing or decreasing. We just care, is it getting closer to 0 or further from 0? And from here to here, is x getting closer to 0 or further from 0?
It's getting closer to 0.
Yeah, we're approaching equilibrium, so the distance from equilibrium is shrinking. So the spring potential energy should be decreasing as well. In fact, we could even list initial and final values. And x initial is x1, x final is 0. And we don't have a numerical value for x1, but we can just leave it as a variable. And what else is changing in the meantime?
Kinetic, it's increasing.
We definitely have a change in kinetic energy. We can tell it's increasing partly because we started at 0 and you can only get faster from there unless you stay at 0. Also, the spring potential energy is decreasing. So unless this is an open system, we should expect something to be increasing as well. We can even list the initial speed being 0 and the final speed we don't know, but that's what we're trying to find. And should we treat this as an open system or a closed system?
I would say a closed system.
Yeah, I think a closed system makes sense here.
I do have a question regarding that, though. Say, for the sake of argument, they said, oh, friction is also involved.
Mm-hmm.
Would that make it an open system, or could you include the friction and make it once again another closed?
Yeah, it really depends, as you say, on whether you include it or not. If you specifically, the friction is presumably going to be sort of leaching off of the mechanical energy and turning it into thermal energy, or maybe bond energy if this is like on a surface made of ice that's already at 0 degrees, for instance. But generally, friction has the effect, or at least sliding friction, has the effect of converting mechanical forms of energy into internal forms of energy, usually thermal, sometimes bond energy. So in that case, you could treat that as a closed system by including thermal energy in the system. You'd have this one, it's like spring potential energy decreasing, kinetic energy maybe increasing, but not increasing as much as you'd expect, and thermal energy also increasing as the system gets warmer. Or you could leave thermal energy out of the system and treat it as an open system with heat leaving the system. In either case, we're talking about a transfer of energy from mechanical systems to internal systems. The difference is, do you want to treat the internal systems as thermal energy in the system, increasing, or do you want to treat the internal energy as not included in the system, but instead you've got heat leaving the system? Either way works. It's really just a matter of what you're trying to figure out versus what you'd like to ignore. In this case, though, we're assuming the surface is frictionless, so we can ignore that entirely. Any other questions on the setup so far? So if we turn this into an equation, what should we assume about these changes? if it's a closed system.
It equals 0.
It's equal to 0.
Yeah, those changes have to add up to 0 because we get no total change. There's no energy entering or leaving the system. It's only changing form within the system. And then we can fill in our usual formulas for each of these. For the spring, we've got our usual 1/2 times K times the change in displacement squared. For a change in kinetic energy, we've got our usual 1/2 times the mass times change in speed squared. And I would recommend leaving these as variable. Well, I guess in this case, we have to leave them as variables because we don't have specific numbers. But in general, I think it's usually a good idea to leave everything in terms of variables until the very end. Solve algebraically in terms of just variables, and then plug in numbers if you have them. One exception though, in this case, some of the initial and final values happen to be zeros. It is often a good idea to plug in zeros if you can, because that's not just like, well, it's just 3 by coincidence. 0 means something important. 0 means it's not moving, or 0 means it's at equilibrium. 0 usually has some real physical meaning there. So if we fill that in, delta x squared, so that'll be final value squared minus initial value squared, 0 squared minus x1 squared, and then 1/2 times the mass. And we've got to be careful about mass here. What mass would we be using?
The mass would be 2m in this case, right?
You've got these two objects, A and B, and I think we're assuming they're the same mass.
Yeah, they both have mass m.
Yeah. So if each one has mass m, then mass is actually going to be 2m. So that's 2 times the mass of each one. And note that in the initial situation, we've got these m and m attached together, so we can treat them as just one object with mass 2m. At the end, the glue has just broken, but the simple act of the glue breaking doesn't really change anything. After this situation, A and B are going to have to be treated as separate objects. But at the instant the glue breaks, we can still treat them as the same object because they haven't separated yet. All that's going on is the glue has broken, but they're still moving at that same speed right that instant. So we're going to treat it as a single object of mass 2m at initial and final situations. And then unknown final speed squared minus 0 is the initial speed squared. Any questions on the equation so far? And then if we simplify this a bit, we've got 1/2 times k, and then 0 minus x1 squared is just negative x1 squared. So negative 1/2 k x1 squared. 1/2 and 2 cancel out, so we get m. And then v final squared minus 0 is just v final squared. And what are we trying to solve for here?
V final.
So to isolate v final, we're going to want to, we've got this negative term being added, so we add its opposite to both sides. So add 1/2 k x1 squared to both sides, and we get m times v final squared equals 1/2 k times x1 squared. And then what else do we need to do?
Divide by m.
Divide by m. So v final squared equals 1/2 k becomes k over 2, and then we get an m in the denominator since we're dividing by m times x1 squared. And as one last step,
let's take the square root.
Yeah, take the square root of both sides. And if you've got just multiplication and division, you can split up that square root. Square roots do not split up over addition and subtraction, but square roots can be split up over multiplication and division. Square root of v final squared is just v final. Square root of k over 2m is just a constant. And then square root of x1 squared is x1. So this gives us a formula for the speed at that instant when they're passing through equilibrium. When they're passing through equilibrium, their speed is going to be square root of k over 2m times wherever they were pulled back to in the first place. Why we did 2m, yeah, that 2m in step 3 is because this object, each one of these, block A and block B, each have mass m. So this can be treated as one object with mass 2m, since there's two copies of the same block. So that's where we get the 2m. The mass of that object is 2m. Yeah, exactly. We're just adding them together because we're treating them as just one combined object. To calculate block B separately, the thing is, at the instant when they separate, both of these blocks are going at this speed, each one individually. After they separate, are there any forces acting on block B? It's not really attached to anything anymore, right? As soon as block B separates, block B has this final velocity, square root of k over 2m times v1, or x1, I should say, the speed we just found. And since B is no longer attached to the spring, there's nothing that's going to slow it down or speed it up, especially since there's no friction either. Block B is just going to keep coasting at the same speed forever until it hits something. So we can assume that after the break, block B just keeps moving with this exact same speed. But then what's going to happen to block A? Can block A just keep moving at that same speed forever?
It's going to get pulled back, right?
As soon as block A passes equilibrium, the spring, which is still attached to block A, is going to start pulling back and will start slowing down. So B, having broken off, continues with this same speed forever. But A is going to start slowing down. A is going to get slower and slower and eventually come to a stop at some final maximum stretch location. And then it'll bounce back. But I think there's another part of the problem asking how far does A stretch the spring on its own? Wouldn't block B go faster? The thing is, the separation, the physical act of separation here doesn't change the speed. It's not like B is kicking off from A. They're moving together and then they separate. A slows down and comes to a stop, but B just keeps going. There's nothing causing B's speed to change. And you got to keep in mind that in the kinetic energy formula, if you transition from AB as an object to just B as an object, you would think of it as the mass has decreased. But there's no reason to assume the kinetic energy stays the same. Object B on its own does not have the same kinetic energy as the combined object AB together. So when they separate, they split up the kinetic energy, presumably half and half because they have equivalent masses. So when they separate, A gets half the kinetic energy, B gets the other half of the kinetic energy, and they're both traveling at the same speed at that instant. But the difference is B is going to continue coasting with that same speed, and A is going to slow down and come to a stop. Any other questions on that so far?
I have a question, but it's related to friction. So I don't know if this is part of that midterm question, but let's say that the surface was not frictionless. How would the algebraic formula or equation differ? And I know you were saying it could either be heat leaving the system or mechanical energy being transferred to internal energy. So how would you then set that up?
Well, like you said, there's two ways to do it. Algebraically, what that would look like, if you treat it as an open system, like if you treated this as an open system with work leaving the system, then instead of having the changes add up to 0, you'd have the changes add up to work, specifically the work done by friction. And how would we represent the fact that work is leaving the system? What would that tell you about the value of W?
It has to be negative.
Yeah, W would be a negative value. We wouldn't write a negative sign here. We're still talking about the changes add up to the amount of work. It's just that the work would be a negative value. Like the value of that variable would be a negative number.
Right, so then would the spring potential energy and the kinetic energy, it would still, those would be positive. Oh no, one of them would be negative and one would be positive.
Yeah, I would expect because we're definitely decreasing the spring potential energy as we move towards equilibrium. The kinetic energy is presumably increasing. I would guess it's going faster than 0 at this instant, unless it has really come to a complete stop.
Okay.
But these are no longer going to add up to 0. We're going to have presumably a large decrease in spring potential energy for a large negative. And then kinetic energy wouldn't be increasing as much as we'd expect. We'd get a small positive here. Large negative plus small positive adds up to a negative amount of work.
And did you choose work instead of heat for any specific reason?
Yes, because friction is a force. As the object slides on the ground, it's experiencing a force of friction acting against the direction of motion. Like if it's moving to the left, then the force of friction is pulling to the right. It's a drag force. So since work is acting against the motion, work is trying to slow it down or prevent it from getting faster, we would treat that as work leaving the system. And since friction is a force acting on this object that's moving, and we're defining work as force times distance, how much force times how far it has traveled, then friction would count as work. And the reason why we treat it as negative mathematically is if the force and motion are in opposite directions. Like let's say it's moving to the left, but the force is to the right. Moving to the left means delta x would be negative. Force to the right means F would be positive. And negative times a positive gives you a negative result. So in general, if the force and motion are in opposite directions, you get a negative amount of work. If the force and motion are in the same direction, you get a positive amount of work. Any questions on that so far? The alternative, oh yeah, go ahead. Was there another question there? Okay, what I was saying is the alternative way to do this would be to ignore work and instead treat it as thermal energy increasing as part of the system. If you include thermal energy in your system, we could still treat it as a closed system. We would just include a delta E thermal representing some of the energy turning into thermal energy as a result of friction. So we still have spring potential energy decreasing and kinetic energy increasing, but the kinetic energy is only increasing a little bit, and the other increase is the thermal energy increasing. So we might have something like a large decrease in spring potential energy converting to a little bit of increase in kinetic energy and a little bit of increase in thermal energy. So the object is getting faster, but not as fast as we would expect. Instead, it's also getting warmer. And note that in both cases, we end up with the potential energy and kinetic energy behaving the same way. In both of these approaches, we have a large decrease in spring potential energy and a small increase in kinetic energy. The only difference algebraically is, are we putting the friction as delta E thermal as a positive on this side, or are we putting friction as work as a negative on the other side? And a positive on one side of the equation and a negative on the other side of the equation are algebraically equivalent anyway. So you get the same result. Any other questions on that so far? And if you wanted to know actual numerical values for friction, you need to have some more information. One possibility might be maybe you know the force of friction and you know the distance traveled. If you know both of those, you can just multiply them together to get the amount of work and fill that in the equation. Or alternatively, maybe you don't know the force of friction, but you know the starting location and ending location and the starting speed and ending speed. So you can fill in everything else in the equation, the positions and the speeds, and then work would be the only unknown left. Any other questions on that so far? All right. And then beyond that, if you wanted to figure out, for instance, how far A stretches the spring, you could use this final setup as the initial of the new problem. And then the new final would be A stretched all the way out as much as it can to some new location and now going at speed 0. And take a look at that one. FNT6 number 1. Let me pull that up. And there was a question on graphs of potential energy. I want to make sure I get to that also. For problem 6, or FNT6 problem number 1, I think it would be a very similar setup. We have, we know a mass of an object, we know the spring constant, we know it's stretched to a certain distance and released. And you want to know what's the speed as it passes some other location.
Yeah, it's the only thing that I have with that question is if I set it equal to 0 or if I'm going to set it to like the force.
Usually you'd set it to work plus heat because it's energy transfers. But it says assume the transfer of energy to thermal systems is negligible. So in part A, I would assume that there is no friction at all.
So set that one equal to 0?
Yeah, because in part A, we can treat it as a closed system.
Perfect. That's all I needed.
Yeah, then at B, it says we're assuming that we do have friction. But this is one of the examples where it says we know it starts off stretched to 48 centimeters. And we know it ends up stretched only to 40 centimeters. Also, we're assuming that it starts off at rest because it was just released. And also it ends up at rest because we're assuming that 40 centimeters after one oscillation, 40 centimeters is the furthest it gets. And it gets to 40, comes to a stop and bounces back. Or I guess on the compressed side. So that would really be in the opposite direction. It is compressed to, and we might call that negative 40. But we're going to be squaring the x value anyway, so the negative doesn't matter. But we release it from 48 at speed 0. It gets faster and faster, passes through equilibrium, gets slower and slower, comes to a stop at 40 centimeters on the other side. So this would be the sort of situation where we know the starting location, we know the ending location, we know the starting speed and ending speed. Although if the starting speed and ending speeds are the same, what does that tell us?
That kinetic energy is 0, basically.
Yeah, we've got no change in kinetic energy at all.
Yeah.
So in this case, our entire energy interaction diagram is just going to be potential energy of the spring.
And would that be equal to 0?
The changes, because we're treating, first of all, from 48 to negative 40, is the distance from equilibrium increasing or decreasing?
It's decreasing.
Yeah, because absolute value of 40 is smaller than absolute value of 48. So if we list out initial and final, we've got initial equals 48 centimeters. We should probably convert these to meters so it matches up with the other units. X final would be 40 centimeters or 0.4 meters. And again, that's going to be negative, but since we're going to be squaring it anyway, it doesn't matter. And there's no change in kinetic energy because we start and end at speed 0. Are there any other types of energy that are changing?
Thermal energy.
Yeah. And again, we can treat thermal energy as part of the system, or we can treat that as work leaving the system. But this question is specifically asking, find the increase in thermal energy. So I would go ahead and treat thermal energy increasing.
Part of the system.
Exactly.
Yeah.
And formally, the indicator would be temperature, but we don't really have enough information to find any temperature changes because we don't know if that's the block getting hotter or the spring getting hotter or the tabletop getting hotter or the air around it getting hotter. All we know is one or more of these objects are gaining thermal energy. We're just going to lump all that together as an increase in thermal energy. And if we do include thermal energy, are we now treating this as an open system or closed system?
Would this become an open system?
So heat
because...
is leaving or entering, or work is leaving or entering?
Wait, can you repeat the question? Sorry.
If we are including thermal energy, are we now going to
Yes.
treat this as an open system or a closed system? Are there any forces doing work?
Oh no, it's still a closed system.
Yeah, if we are including thermal energy, I would treat this as a closed system.
Yeah, because
If you're saying potential energy alone is your system, then that would be an open system because friction is decreasing potential energy and taking it somewhere else.
yeah,
But somewhere else that it's going is the thermal energy.
yes,
So if we include both of those, this is a closed system.
that makes sense. Thank you.
And then we can set up our usual change in potential energy plus change in thermal energy. And since we now have a closed system, that's going to equal 0.
0.
And in this case, I wouldn't bother filling in a formula for delta E thermal. We don't really need an MC delta T because we're not trying to find a delta temperature. We just want to know the delta E thermal.
Yes.
So subtract this from both sides, fill in your values, and that'll tell you what the change in thermal energy is.
Perfect. Thank you so much.
Any other questions on that one? All right, then let's take a look at the idea of graphing potential energies. What we've been looking at so far is just comparing initial and final values. And that can be really useful if all you care about is the initial and final values. You don't have to worry about all the stuff that happens in between. But it can also be something of a disadvantage because it doesn't tell you any information about what happens in between. And this is where the idea of graphing the potential energy can be a very useful visual tool of figuring out what's happening. For example, if we're talking about, let's say, let's go ahead and continue with that mass on a spring. Potential energy for a spring is 1/2 times spring constant times x squared. Instead of just looking at initial and final values, let's try actually graphing that. If we make a graph treating location or displacement as the independent variable and energy as the dependent variable, because energy is a function of x here, what would this graph look like? If we were to actually graph 1/2 kx squared, yeah, we'd get a parabola. The x squared would generally graph as a parabola. The 1/2 k is just a constant multiplier, so that's going to change the steepness of the parabola, but it's not going to change the fact that it's a parabola. And specifically, it would be a parabola whose vertex is where? Yeah, vertex at 0, 0, the origin, because we don't have any other modifiers. If we had like a plus something x or a plus something, or if something was being added or subtracted to x before we square it, that would move the vertex around. But if it's just something x squared, the vertex is at the origin. Since k times 1/2 is positive, it's going to open upwards. And you should get a completely symmetric parabola with vertex at the origin. And again, the steepness, like how quickly it's rising, is going to depend on the value of k. So a stronger spring is going to have a steeper graph, a weaker spring is going to have a flatter graph. But it's always going to be a parabola for spring potential energy because of the x squared. And if you have a value for k, you could even make a more accurate graph. You could choose some x values, plug them in, calculate the potential energy values, and graph it point by point. It looks like what people were asking about earlier was the forces here. So let's see how we can interpret this as force. What's the one concept we've seen so far that relates force and energy? How are force and energy related to each other? Like if you've got, let's say, a moving object and you apply a force to it, what are you doing to it? What does that count as?
You're doing work.
Yeah,
right?
A force on a moving object counts as work, and work is a transfer of energy. So if we go back to the idea of work, work is a transfer of energy. In fact, more generally, we would say that in an open system, delta E total is work plus heat. But let's simplify this. Let's say we set up an experiment where we only want to make one change. Like let's say you've got this object attached to a spring. And what you're going to do is you're going to push on this. You're going to apply a force. And you're going to move this object. As you move it, what types of energy would you expect to be changing?
Kinetic or spring potential energy, actually.
Yeah, we got potential energy of the spring changing because we're compressing the spring. We could also have kinetic energy changing because maybe it's getting faster. But let's focus on just the potential energy. Is there any way you can make sure that only the potential energy is changing and the kinetic energy is not changing?
Yeah, so if it's moving at a constant speed.
Yeah, let's set up the experiment with the assumption that the block is moving at a constant speed. Let's say you're pushing the block at a constant speed. So you're just steadily pushing it. And of course, as the spring compresses, you're going to have to gradually push harder and harder. But let's say you're pushing exactly enough so that the block moves forward at a constant speed and does not get faster or slower. So that means there's no change in kinetic energy. It has a little bit of kinetic energy. It is moving. But if we assume that we're pushing it so that it moves at constant speed, then there's no change in kinetic energy, which means delta E total is only change in potential energy. There's no change in kinetic energy because it's moving at constant speed. And as you push, you are doing work to it. But there's no heat because we're assuming there's no transfers of energy because of temperature difference. It's not like we're exposing this spring to a pot of boiling water or something. We're only looking at a mechanical transfer of energy, which we can now write as force times distance, since that's the definition of work. And that's specifically the force that you apply. The force that you apply to the object times the distance that it travels. However, why do you have to apply a force in the first place? Why can't you just give it an initial shove and then let it coast? Is there a reason we can't just let this drift forward on its own?
Is it due to friction?
I think we can assume there's no friction here, because we don't want to worry about extra work done by friction or changes in thermal energy or anything. We want to look at just the potential energy. But yeah, the spring itself is exerting a force. In fact, the reason why we can treat the spring as being involved in potential energy in the first place is because when you push on it, the spring itself is exerting a force. So if you look at the block, we've got the force you're applying. So you're applying a force to the right. Your applied force, but you're pushing back against the force from the spring. As the spring gets compressed, the spring pushes back to the left. The spring pushes outwards, away from the direction you're pushing. So you're pushing in one direction, the spring's pushing in the other direction. If we're assuming that there's no change in speed, what has to be true about these forces in order for the spring to not change its speed? Yeah, they have to be equal, at least equal in magnitude and opposite in direction. So the fact that there's no change in speed means the forces cancel each other out. That these two forces added together equals 0. In other words, the spring force is the exact opposite of the applied force. So the force you apply has to be exactly the opposite of the force of the spring if we're assuming this is moving at constant speed, which means we can make a substitution. Change in potential energy equals, instead of writing applied force, we can write opposite of the spring force. So the change in potential energy as this block moves is negative spring force times delta x. Any questions on that so far?
But that would only be the case if this was moving at a constant speed, right?
Well, we're focusing on assuming it's a constant speed so we can ignore kinetic energy and focus on just potential energy. But if it is changing its speed, you'd be applying more force and there would be a change in kinetic energy. So the extra force you're applying beyond canceling out the spring force would go into increasing kinetic energy. In general, the force you're applying just to cancel out the spring force goes into increasing the potential energy. Any more force you apply beyond that goes into increasing kinetic energy. But in many cases, it's useful to set up an experiment, even if it's just a thought experiment, where only one thing is changing, so you can focus on just what's causing that change. That also makes our applied force much more predictable. We can say, because we're treating this as going at constant speed, we can assume that the applied force is exactly the same as the spring force, but in the opposite direction. If you then solve that for spring force, what do you get? How would you isolate force of the spring here?
So negative change in potential energy divided by delta x.
Yeah, we just divide both sides by negative delta x, and we get an expression for force of the spring. Force of the spring is negative change in potential energy over change in x. Any questions on the algebra there so far? So one way to interpret this is that the amount of force is describing how quickly the potential energy is changing. It's a rate of change. But note that it's not a rate of change with respect to time. Force is not describing how quickly the potential energy changes as time passes. Force is describing how much the energy changes per meter of distance traveled. So for instance, if the force is 10 newtons, that means the potential energy changes by 10 joules per meter traveled. It's a rate of change with respect to distance. And since potential energy and distance are the variables on this graph, what would change in energy over change in distance tell you about the graph itself? What would we call a change in energy divided by a change in position?
The slope, right?
Yeah. This ratio is the slope of the potential energy graph. A force associated with a potential energy is negative delta PE over delta X. In other words, negative slope of potential energy graph. So the rate of change, that is the slope of the potential energy graph, tells you how strong the force is. For example, if we compare the slope, and really we shouldn't be talking about slope like from a point to a point. That's good, that's great for an average value, but we don't want a slope from point to point. We want a slope of what sort of line? Like, does this line from point to point, because you need 2 points to establish a slope, does that line tell you accurate information about the curve itself? If you want to get a slope or something like a slope at a single point, you don't want a secant line that passes through 2 points like that. You want what kind of line? Think back to calculus. Yeah, we want a tangent line, right? In calculus, the change in y over change in x gives you an average rate of change, but the derivative, we should really be treating this as a derivative, the instantaneous rate of change. Derivative of potential energy with respect to x, that's the exact value of the force. If you take any location on the graph and draw in a tangent line, a straight line that matches the curvature of the graph as close as possible at that point, the slope of that tangent line is the derivative of the function. And what that tells you is how strong the force is. Of course, this negative sign is also going to influence the results as well. Like in this case, the tangent line has a positive slope. So what does that tell you about the force? If the slope is positive, then the force is going to be
negative,
which matches up with the idea that if you stretch the spring to the right, the spring exerts a force pulling back to the left. Alternatively, if we're talking about like this location over here, we've got a negative slope for the tangent line. A negative slope is going to translate to a positive force. In other words, if you compress the spring to the left, the force of the spring is going to be pushing back to the right, pushing in the positive direction. So the direction of the force is the opposite of the slope of the tangent line. But the magnitude of the force is determined by, that is how strong the force is determined by how steep the tangent line is. Like right here, the tangent line is kind of steep, so you get a kind of strong force. Over here, the tangent line is much more steep, so you get a much stronger force. Is there anywhere where you would experience no force at all? Any place where the slope would be 0?
At 0, at equilibrium.
At that equilibrium location, since we reach a minimum, anytime you're at a minimum or a maximum of the function, yeah, you get a slope 0. Slope 0 tangent line means the derivative is 0, which means the force is also 0. And this is really what we mean by equilibrium. An equilibrium location is a location where the force is 0, which translates to a max or min on the potential energy graph because the slope is 0. But this is, in general, how force is related to potential energy. The force is associated with the slope of the potential energy graph. And any potential energy is linked to some kind of force. Spring potential energy is linked to the spring force. Gravitational potential energy is related to the force of gravity, and so on. Any questions on that so far? All right, see if you can do the same approach on your own with gravity. Like try graphing potential energy equals m times g times y, with y as the horizontal axis and energy as the vertical axis. And see if you can do this same sort of approach. And then we'll look into some more examples of how to use that next time. See you then.
Thank you.